Is gravity the hidden key to quantum physics? The suggestion that gravity might hold the missing piece to understanding quantum physics is one of the most intriguing ideas in modern theoretical physics. In this essay, I'll explore what that means in plain English, why gravity and quantum mechanics are disconnected today, how gravity might serve as a bridge or key, what the evidence and theories suggest, and what it would mean if gravity really is the hidden key. The puzzle: two great theories that don't mesh. On one side, we have quantum mechanics and quantum field theory, which describe the subatomic world of particles, fields, probabilities, and uncertainty. On the other, we have general relativity, which describes gravity as the curvature of space-time on very large scales. Both theories are enormously successful in their domains, yet they clash when you try to unify them. For example, quantum theory assumes a fixed space-time background. General relativity treats space-time itself as dynamic. Thus, the key question becomes, how can gravity be reconciled with the quantum world of the very small? Many physicists believe that gravity is not just a nuisance, but might provide the clue to unlocking a unified description of reality. Here are some reasons why gravity is more than just another force. It might be the pathway to quantum physics. 1. Gravity is the outlier among fundamental forces. The electromagnetic, strong, and weak forces have quantum descriptions. Gravity stubbornly resists that framework in simple form. 2. Gravity touches space-time itself. Unlike the other forces, gravity influences the structure of space and time. It is geometry. That means if you want a quantum theory of everything, you likely need to figure out how space-time becomes quantum or emergent. 3. Gravity at extreme scales enters the quantum realm. In black holes, the Big Bang, Planck scale physics, gravity and quantum effects force each other's hand. That region is where the hidden key might be found. 4. Some theories suggest gravity emerges from quantum processes. There are frameworks where gravity isn't fundamental but arises from quantum information, entanglement, or other deep quantum phenomena. If true, then gravity is the bridge rather than the obstacle. Promising theoretical ideas. Here are a few of the conceptual frameworks that aim to bring gravity into the quantum fold, or show how gravity may be the clue. Quantum gravity research. This is the broad field trying to quantize gravity, find a graviton, or formulate a theory where space-time is discrete. Emergent gravity/entropic gravity models. Some scientists explore the idea that gravity emerges from thermodynamics or statistics of microscopic degrees of freedom. Experiments probing gravity at small scales. Measuring gravitational interaction in the quantum regime is extremely hard, but recent work hints at steps in that direction. Algebraic and black hole frameworks. Some research proposes that black holes might be the bridge between quantum and gravity because they demand both quantum and gravitational descriptions simultaneously. The key questions and obstacles. While the idea that gravity might be the hidden key is tantalizing, it's not without major hurdles. Lack of experimental evidence. We have very few direct observations of gravity behaving in explicitly quantum ways. That makes claims speculative. Mathematical incompatibilities. Gravity, as described by general relativity, is a continuous, geometric theory. Quantum mechanics deals in probabilistic, discrete processes. Merging them leads to infinities, divergence, and breakdown of standard methods. Which side gives? Do we need to quantize gravity, or do we need to revise quantum mechanics to include gravity? Some theorists propose that maybe gravity isn't quantum after all. Interpretational challenges. If gravity is emergent, what are the underlying quantum degrees of freedom? What is space-time made of? These are deep metaphysical as well as physical issues. Scale problem. The energy scales at which quantum gravity effects become significant are far beyond current experimental reach. That slows empirical progress. What if gravity is the hidden key? What would it mean if we discover that gravity is the missing piece in quantum physics? Here are some possible implications. A unified framework. We could arrive at a theory of everything that explains all forces, particles, and space-time in one coherent model. New physics. We might find new particles or new phenomena. Technological spin-offs. Though speculative, being able to handle quantum gravity might lead to breakthroughs in quantum computing, materials, or even space-time engineering. philosophical shifts, our understanding of space, time, and matter could radically change. If gravity emerges from quantum information, then reality is more interconnected and less stuff in space than we think. Cosmological insights, origin of the universe, black holes, dark energy, and dark matter might be woven into this unified description, giving answers to some of the greatest mysteries in cosmology. My perspective, from where we stand now, I believe gravity could indeed be the hidden key, or at least a major part of it, but I don't think we've unlocked it yet. What we're seeing is a series of clues pointing toward gravity's special role, experiments inching nearer to quantum gravitational regimes, theoretical models that show how gravity might emerge, and a persistent mismatch between the quantum and gravitational worlds that demands a deep resolution. For someone like me, engaged in detailed technical thinking, it means the frontier is exciting. The next decade may bring bench-level tests of quantum gravity or breakthroughs in emergent gravity models. It may even shape how we design algorithms, simulate physics, or interpret data in fields like quantum computing or materials science. But for now, the term hidden key is still aspirational rather than confirmed. We may be hunting for the key in the dark, but there's real hope that it's right behind the next theoretical door or experimental threshold. Conclusion: yes, gravity could very well be the hidden key to quantum physics. It has the unique status of altering space-time itself, resisting quantum treatment, and showing up in the extreme regimes where quantum and relativistic effects collide. But the key turn has not yet happened. We still need robust experimental evidence, mathematical clarity, and conceptual consensus. If we succeed, the payoff is enormous. A unified vision of the cosmos, new physics, and a deeper grasp of reality than ever before. In that sense, the hunt for gravity's role isn't just about understanding one force. It's about unlocking the underlying code of the universe. In the words of a physicist, we know two halves of the story, quantum mechanics and gravity, but we haven't seen the connection that ties them into one whole. If gravity is that connection, then finding it will reshape everything we know.